Hello and welcome back. In section 9.3 we have to play with the complex plane and Mth's theorem. So the idea with the complex plane is basically it's similar to our rectangular coordinate system, except the vertical axis represents the imaginary component of a complex number, and the horizontal plane represents the real number component of a complex number. So they basically take on the form of z is x plus yi. So for example, if we're plotting z equals 2 plus 3i, go to 2 on the real, and 1, 2, 3 on the complex. And there's our placement in the complex plane. The magnitude of z which is usually denoted with the z inside of what we'd recognize as absolute value gates, sometimes also called the modulus of z, referring to the same thing. Basically, they're both measuring distance between the origin and point z. So capital being the origin. So modulus of z is just the distance between, for example, our point 2, 3 and the origin. So that would be just the square root of x squared plus y squared. So for example, in our number 2 plus 3i, the magnitude would be square root of 2 squared plus 3 squared. So root 13 would be the magnitude of this complex number. Now we can also work with the polar form of a complex number as before. So just like before, x is our cosine theta, y is our sine theta. So then our z, that in rectangular is x plus yi. In polar would be our cosine theta plus I r sine theta. And in that case, the magnitude of z would also then be your radius for your polar coordinate. Since the radius is also just measuring distance from the origin to a given point. So for example, they might give us a z is 2 plus root 3i, or I root 3. I usually write my i's in front when I have a radical involved, or throw the radical in parentheses. Just to emphasize, the I is not under a separate square root. I is under its own square root already. So as far as plotting that, we'll just rough this in here. So I'll go to 2, square root of 3 is about, what's that, 1.7 and change. So about 1 3/4. So here's our location. And our magnitude, which will also be our radius. Square root of 2 squared plus root 3 squared. So that would be square root of 4 and 3. So root 7 would be our radius. So recalling that x is equal to r cosine theta. So then I can say that 2 is equal to r root 7 times cosine theta. So cosine theta is 2 root 7 over 7. So 2 over root 7 and rationalize. Y is r sine theta. So our y is root 3. So root 3 is root 7 sine theta. So sine theta is root 3 over root 7, which rationalizes to root 21 over 7. So then turning this into polar form, we would take the arc cosine of 2 root 7 over 7 or the arc sine of root 21 over 7. Either way, theta is approximately 40.89 in degrees. So then our polar coordinate form would be r, so root 7 cosine of about 40.89 degrees plus I root 7 sine of about 40.89 degrees. So that's the polar version of the 2 plus I root 3 that we saw in rectangular form. So let me look at a couple cute little proofs for complex products and quotients. You've already done the rectangular version in your college algebra, so we'll just worry about the polar version. So we're looking at two complex numbers, so we'll call them z1 and z2. So z1 is going to be radius 1 cosine theta 1 plus I radius 1 sine theta 1. And complex number z2 radius 2 cosine theta 2 plus I radius 2 sine theta 2. So z1, z2. I can factor an r1 from my z1. I can factor an r2 from my z2. So our product z1, z2, I would multiply the radii and then just FOIL these guys out. So cosine theta 1, cosine theta 2, plus I times cosine theta 1, sine theta 2, plus I sine theta 1, cosine theta 2, plus I squared sine theta 1, sine theta 2. And we'll pretend I have enough room to close my parenthesis there. So z1, z2. I'm going to hang on to the r1, r2, and then we're going to do a little bit of regrouping. So I'm going to hang on to this cosine theta 1, cosine theta 2 for the moment. I squared, though, we're going to remember is a negative 1, so minus sine theta 1 sine theta 2. We're going to group those guys together. We'll do the same thing with these middle guys. Each one of them had an I attached. And then we have our cosine theta 1, sine theta 2, plus sine theta 1, cosine theta 2. Now hopefully you recognize this. So z1, z2, we can do a little simplifying. Radius 1, radius 2. Cosine alpha, cosine beta, minus sine alpha, sine beta. That is the cosine of alpha plus beta. So this is cosine of theta 1 plus theta 2. Similarly, hang on to this plus I. Cosine theta 1, sine theta 2, plus sine theta 1, cosine theta 2. This is the sine of the sum. So this would be how we would find our products in polar form. We can do a similar kind of argument with quotients. We would just use a conjugate argument at the bottom. So z1 over z2. I'm going to go ahead and skip to having already factored the r1 and r2. So we'll have cosine theta 1 plus I sine theta 1 over cosine theta 2 plus I sine theta 2. So remember, I is a square root. So think of rationalizing the denominator just like you did when you had the rectangular version in your college algebra course. So we would multiply by 1 using the conjugate of that denominator. So cosine theta 2 minus I sine theta 2. If I do that to the bottom, I also have to do that to the top. That way we change the look, but not the value. We've multiplied by something worth 1. Okay, so a little bit of foiling in our future. Something you can do in your sleep at this point. So we have cosine theta 1, cosine theta 2. We have minus I cosine theta 1 sine theta 2 plus I sine theta 1 cosine theta 2 minus I squared sine theta 1 sine theta 2. Again, we'll do a little regrouping on the next step. Downstairs foiling out, we have cosine squared theta 2 minus I cosine theta 2 sine theta 2 plus I cosine theta 2 sine theta 2 minus I squared sine squared theta 2. Of course, the middle and the bottom drops. That's why we use the conjugate there, and I squared is a -1 minus -1. We'll kick that over to a plus sign downstairs. So z1 over z2, r1 over r2, times at the bottom cosine squared theta 2 plus sine squared theta 2. There's a nice, neat, pretty 1 in the denominator now, attached to our r2. Again, a little bit of regrouping like before. Cosine theta 1, cosine theta 2. Minus a -1 turns into a plus, so plus sine theta 1, sine theta 2. Group those guys together, and then similarly hang on to our plus I. Sine theta 1 cosine theta 2 minus cosine theta 1 sine theta 2. close that on up. So that's a 1 down there, and here's more of the products and sums. So cosine A cosine B plus sine A sine B is the cosine of A minus B, so cosine of theta 1 minus theta 2. Sine times, similarly here, sine A cosine B minus sine B cosine A. That is sine of A minus B, or in this case, theta 1 minus theta 2. So they're nice little derivations to get the formulas out of these guys. So then we end this section on de Moivre's theorem that lets us deal with raising to powers and taking roots. Now, z to the n is r to the n times cosine of n theta plus I sine of n theta. So a complex number to the nth power, this is how we find it. So for example, if our complex number was root 3 by cosine of 5 pi over 18 plus I sine of 5 pi over 18, quantity raised to the 12th. Here's my z, and we're raising it to the n of 12. So we have root 3 to the 12th cosine of n theta, so 5 pi over 18 by 12, plus do the same thing with the i's. So root 3 to the 12th is the same as 3 to the 6th. And we have cosine of, so this is 2/3 of 5 pi, so 10 pi over 3, plus I sine 10 pi over 3. So 3 squared is 9, so this is the same as 9 cubed. So we have cosine of 10 pi over 3. We'll just sketch a quick unit circle on there. So here is 3 pi over 3, 6 pi over 3, 9 pi over 3, so here is 10 pi over 3. So the cosine of that is -1/2. Sine of that is negative root 3 over 2. So 9 cubed, 81 by 9, 729. So negative 729 halves minus 729 root 3 I over 2. So that would be our 12th power. So we can also use de Moivre's theorem to work the other way and work on some complex roots. So we're going to let W be R by cosine theta naught plus I sine theta naught. We're going to let n be at least 2, since we're going to be taking an nth root. And we're going to be assuming that W is non-zero. When that's the case, then there exist n distinct complex roots of W. So the formula will take zk, z sub k, nth root of r, cosine theta naught over n. So square root n is 2, cube root n is 3, fourth root n is 4, and so on. Plus 2k pi over n. And do the same thing with your I sine theta. And here k goes up to n minus 1. So for example, we might look for the complex fourth root, roots plural, of root 3 plus I. So I'll start by turning this into polar, since this is in, our directions are in sines and cosines. So our polar version will find the magnitude. So square root of x squared plus y squared so we have a radius of 2. So then z is root 3 plus I. If I'd like to pull the radius of 2 from that, that means each of these guys is going to be over a 2. So I'm looking for what angle has a cosine of root 3 over 2 and a sine of 1/2. That is pi over 6. So z is 2 cosine pi over 6 plus I sine pi over 6. So there's our format for our basic number in the polar with the desired radius of 2. So then we're just sort of following the recipe here. So this is theta naught. So a fourth of pi over 6 is pi over 24. So then z naught, we're looking for a fourth root. So fourth root of our radius, fourth root of 2. Cosine of, as we discussed, a fourth of pi over 6 is pi over 24. Plus 2 times k at the moment is 0. Two times 0 pi over 4. Do the same thing with your i's. So z naught, fourth root of 2 cosine pi over 24 plus I sine pi over 24. So z1, same kind of format. Fourth root of our radius of 2. Cosine of theta naught over 4 is still pi over 24. Now we have plus 2 times 1 pi over n is still 4. And we have the same thing going on with our I sine theta. So z sub 1 fourth root of 2, cosine of, we have pi over 24 plus pi over 2. So that's 12 pi over 24 plus 1 pi over 24, so 13 pi over 24. Plus I sine 13 pi over 24. So there's another fourth root of our original complex number. Z2, fourth root of 2, cosine of pi over 24, so that's theta naught over n, plus 2 times 2 pi over 4. And do the same thing with your i's. So z sub 2, fourth root of 2, cosine of 4 pi over 4 is pi, so that's 24 pi over 24 plus 1 pi over 24, so 25 pi over 24 plus I sine 25 pi over 24. And last but not least, our Z3. Still the fourth root of 2, cosine of pi over 24 plus 2 by 3 pi over 4 plus I sine of the same deal. So z sub 3, fourth root of 2, cosine of, let's see, so that would be 3 pi over 2, which then would be so 3 pi over 2, so that would be 36, so 37 pi over 24 plus I sine 37 pi over 24. Okay, so now we can take powers and roots even when we are in polar form for our complex numbers. So in section 9.3, I would recommend 13 to 61 on the odds. I'll try and write an equivalent one for our My Math Lab fans. If you have questions, please get in touch. Otherwise, I'll see you next time.